Okay, folks, so we did the first topic of this section, which was linear approximations, and now we're going to look at the topic of differentials. To be honest, these are really two sides of the same coin. They're two different ways of looking at the problem. In the first, when we looked at linear approximations, we said, what would the new function output be? And in this one, we will say, what will the change in the output be? So really, we're answering the same question through two different means. The notation on this one, though, I think is a little bit more confusing, so we'll try and suss that out a little bit. So just as a reminder, we use this Greek symbol delta, and that stands for the change in. Okay, so that is given two ordered pairs. Once you think of these two ordered pairs as being on a function, we could calculate the change in x, and we could calculate the change in y. Of course, this is how you got your slope formula way back in Algebra 1. So something to keep in mind, though, is that in the context of differentials, the delta x and the delta y, these refer to the change in the values of the given function, and that function is usually not linear. So we're still going to have a tangent line approximation here that we're dealing with, and it's important that you associate delta x and delta y. Let me be just slightly more careful. Let me just say that delta y goes with the function. The function, whereas what we'll talk about, the differential y goes with the tangent line. Okay. So that's a review of our delta notation. So now what we want to define is we actually want to define this object called a differential. And this is actually a pretty complicated topic, and I don't want to spend too much time on the idea of what a differential is. But we'll see that we can do some interesting algebra with it, and then we'll use this differential to do additional approximations. So this notation, differential x, so it's just the dx that you've seen in our dy dx when we took derivatives, and we're going to keep seeing this differential x quite a bit more in calculus. Anyway, what you can think of it is it's an independent variable referring to the change in the x coordinate along the tangent line of f at a given point. The differential dy then is an independent variable referring to the change in the y coordinate. This is the key here, on the tangent line of f at a given point. Okay, so I'm going to draw a picture here in just a moment to help clarify this. But before I do so, I want to show you basically what our approximation is. So our goal is to find delta y. We're going to use the fact that delta y can be approximated by differential y. That is the big idea with differentials. Okay, and what I want to show you here is, let's do this sort of combination trick of Newton's and Leibniz's notation. And so we have dy dx is equal to f prime of x. Well, up until now, folks, we've always thought of this dy dx as just a single element. We've thought about it as a statement that stands for the slope of the tangent line at a point, the derivative at a point. But now what I want you to do is I want you to actually think of it as a fraction. I've got one element divided by another element. So I'm actually going to treat this as if it's a numerator, and I'm going to treat this as if it's a denominator, which is sort of a clever little trick of notation, I guess. So I'm going to say that differential y, if I multiply both sides by differential x, then I get that differential y is equal to f prime of x times differential x. And this is going to be the way we calculate differential y. Using this notation right here, we'll calculate differential y, and then we make the conclusion that differential y is close to delta y. All right, so I completely agree if you're feeling a little overwhelmed by this notation. I did find this particularly challenging in my first couple passes through this. Okay, so here I've got a point on a curve. Here is the ordered pair x comma y. Okay, well, I end up at a new x value on the curve and a new y value on the curve. So this is the ordered pair x plus delta x comma y plus delta y. That is the new point on the curve that I arrive at. Okay, and let me see if I can move this. I don't know if it'll let me. Yes, perfect. Okay, so let me move that out of the way a little bit. Oops. Okay, and So what is delta x? Delta x is just this distance right here, delta x. And then what is delta y? Again, I think I need to move this, put it right in my way. Let's move this ordered pair out of the way. We'll just take this part of it. Come on. Move that out of the way. And that's that ordered pair. All I've done is move it out of the way. And so this distance right here is our delta y. Okay? So our goal in these differential problems, rather than saying I want to find the new ordered pair or the new y value, which is what we were looking at before, I'm only interested in finding the change in the y values. I want to know what delta y is. So what is the distance? As I move over in an x direction, how much do I move in the y direction? That's the differential question, or that's the delta question that we want to answer. Well, just like in our linearization, finding this point on the curve can be tricky. So rather than doing that, what we're going to do is we're going to talk about finding this point on the tangent line. Okay? And this point on the tangent line is simply f prime of a. Let me make that f prime of x. Since I've labeled this point right here as x, f prime of x times differential x. Okay? Where differential x is this distance right here. So if I multiply the slope of the tangent line by how much I change in the x direction, I'll get this y value right here. So this is the this is the quantity that I'll be able to calculate easily, and this is our differential y. So from this picture, and I know this picture got a little messy real quick, we see that, notice that for small enough values, differential y is approximately delta y. Differential y here is approximately delta y, and we can see that from this diagram. And if you don't agree, if you say, well, that's way too much of a change, just simply bring this point in closer, and at some point the differential y and the delta y will be close enough for you to be satisfied with it. Okay? Okay. So then here's a quick thing that we'll notice. We notice that delta y is approximately equal to f of x plus delta x minus, or excuse me, it equals the new y value, right? This would be the new y value minus the old y value. That gives us the change in the y values. Specifically, if I wanted to know what the new y value is, that's the new y value. So the new y value would be delta y, the change in y, plus f of x. And we're going to approximate this. Let me make that, that's a pretty ugly looking delta. Make that delta look a little better. And we're going to approximate this by differential y plus f of x. So this will be the technique that we use, a combination of this and this approximation. Okay, this was very abstract, and if you're feeling a little lost with this, I completely understand.